Here we'll look at the p-value approach for hypothesis testing. The good news is that the p-value approach, you do the same steps as before, except we just perform one of those steps slightly differently. First step is always the same. We assume that HO is true. So the null hypothesis, we're assuming it's true. What the p-value is, it's the probability of getting a result as extreme or more extreme as our sample produced. And we'll see what that means as we go through the example. When we make a decision whether to reject the null hypothesis, we're going to compare the p-value to alpha, the probability of a type 1 error. Remember that alpha was the case where you send an innocent man to jail, and you want that to be a very small probability. So this is the step that's different. What we're going to do is compare a probability, so a p-value, to alpha. What we did before was we compared a test statistic, a z-score, to the z-star value that you get from alpha. So again, the difference here, the step that's performed differently, is rather than compare z-scores, we're comparing areas or probabilities. That's the difference when we use the p-value approach. Okay, so when we decide whether to reject the null hypothesis, there's the two possibilities. Either that p-value is less than alpha, and that means we would reject HO. Now, essentially what that's going to mean is when we collect our sample, getting that sample mean as extreme as ours is too unlikely if the HO were really true. So when we assume that HO is true, after we collect our sample mean, we're going to see if that sample mean is unlikely to occur if HO were really true. If that sample mean is too unlikely to occur, then we reject HO. On the other hand, if P is greater than alpha, we fail to reject HO. So getting a sample mean as extreme as ours is likely to occur if HO are really true. When we go through the example, you'll see what this will make a little more sense. Okay, so a professor believes that students at their college spend more than 60 minutes per day on social media. The professor may form the following hypotheses based on their belief. Now, I suggest that you think about what the hypotheses would be in this case, and I have them written down for you because you should be able to do it. So the mean time of all students equals 60 minutes. That's the null hypothesis. So we are going to assume that the mean for all students is 60 minutes. And then the claim that the professor is making is that the mean time is greater than 60 minutes. So that's your alternative. Okay, so what we're going to do, suppose that we know sigma is 8 minutes. The professor collects a sample of 40 students and calculates the sample mean to be 61.5 minutes. Test that claim with alpha equals 0.05. Okay, so essentially what we're looking at here is, if the mean really is 60 minutes, so if we assume that to be true, then is producing a sample mean of 61.5 when you choose 40 students, is that sample mean of 61.5, is that unusual or not? If it is unusual, then we would reject HO. If it's not unusual, we fail to reject HO. That's the basic idea here. So what we need to do, just like before, we're going to calculate our test statistic for x bar equals 61.5. Okay, so that's where you use x bar minus mu over sigma over square root of n. And we end up with a test statistic of 1.19. So that's saying that that sample mean of 61.5 produced a z-score that was 1.19, meaning that that sample mean is 1.19 standard deviations above 60. So on a normal curve sketch, we're assuming that 60 is the mean, so that's right in the middle. And 1.19, we know it's on the right-hand side, but we're not exactly sure. What I have here drawn in red is the rejection region using alpha. Okay, so just like before, we have this rejection region. Now, the difference now is, the only step that's different for us, before what we did is we looked up 0.05 in our table, or we did the inverse norm, and we ended up with a z-score of 1.645. Okay, so on a z-axis, we know that 0's in the center there, and an alpha of 0.05. On a z-axis, the z-score, the critical number that went with that, is 1.645. And that's how we established our rejection region for HO. Meaning that if we got a sample mean that was more than 1.645 standard deviations above the mean, so that z-score was greater than 1.645, we'd be in the rejection region for HO. If we got a sample mean that was less than 1.645 standard deviations from the mean, then we would have failed to reject. Now, what's wonderful, and this is why I show you the other way first, because it's easier to understand. Now that we have this 1.645, which we had to do a little bit of work to get that from the 0.05, we had to look that up in our table or use the calculator to get this number. But we know that 1.19 is going to be over in here. That's the test statistic. So now, before, we could have made our decision that we failed to reject HO, and we're basically done with that decision. Now the difference is, rather than look up these z-scores, so ignore those. Now the difference is, we have alpha's 0.05. Now we're going to find the probability of getting a z-score as extreme as this. So in number 2, we're going to find the probability that a sample mean is greater than 61.5. So when we do that, we converted 61.5 into a z-score of 1.19, and then you go to your z-table, and when you look up 1.19, you get 0.8830. Well, that's the area to the left. So you have to subtract that from 1, and you get 0.1170. Okay, so what that's telling us is the area to the right of this x bar value, 61.5, has 10% area, which is more than 0.05. So that means you have more area out here in the right tail for that test statistic. Okay, so the area all the way out here, so from here to the right, is 0.1170. And that value, 1170, is called the p-value, which is the probability of getting a sample mean as extreme as what we've got, if the mean really was 60. Okay, so now what we're doing is, we know that that's the x bar value is 61.5 right here. So now, if we look at what's happening is, we have a p-value, 0.1170, that is greater than alpha. So our decision, the p-value is greater than alpha, we failed to reject HO. And that meant that the sample mean from our sample is likely to occur if HO were really true. So if the population mean really is 60, then it is not unusual to get 61.5 as a sample mean. That's what this is telling us. Okay, so our decision is to fail to reject HO and there is enough, not enough evidence, I have it written down here more nicely, not enough evidence to support the claim that mu is greater than 60. Okay, so again, the only difference is now we are comparing probabilities rather than z-scores. Okay, that's the difference. Okay, on the second page, similar questions. Okay, except now, suppose everything else being the same, we took another sample of 40 students, and the sample mean was 65.8 minutes. Calculate this the test statistic for that sample mean. Okay, and this is the same as before. I'm just going to show you that something different happens here. You end up with a z-score of 4.59, and when you find the probability that z is more extreme than 4.59, so again, we're off to the right-hand side here. We have alpha is 0.05 again. Still had a z-score of 1.645 there for the critical number. But now the p-value is much smaller. So now, getting a value to the right of 4.59 is very close to 0. And what we're using is 0.0002 just from the table of values. When you look it up in the z-score table, the highest that it goes to is 3.49, which is 0.9998. So when you subtract that from 1, you end up with a very small value of 0.0002. Okay, so that 0.0002, your p-value is way to the right here, which is smaller than alpha. Okay, so if p is less than alpha, we reject HO. So that sample mean, getting that sample mean as extreme as ours, is unlikely to happen if HO were really true. Okay, so if the mean really was here at 60 in the center at 60, then getting 65.8 would be very unusual. So that means we reject HO, and there is enough evidence to support the claim that mu is greater than 60 minutes. Okay, so again, rather than compare these z-scores for our rejection region, we're just comparing probabilities. P-value, which is 0.0002, to alpha.